Section R3 mostly has to do with fractions. Reducing fractions, multiplying and dividing, adding and subtracting where you need to get a common denominator, that kind of stuff. So the first thing where you have to simplify a couple of fractions using the reduction property, basically the reduction property is canceling stuff. So really it's just that you would factor the numerator and denominator and see if you get common factors that you can cancel out. So really, the reduction property, it's canceling stuff. And that's what we're going to do. So it would be helpful if I had actual ink. There we go. So 21 over 70. So we could rewrite that. And you don't have to jump right to the prime factorization. Just any kind of factorization would work. Although I guess for 21, you're going to get that because there is no other factorization of 21. And then for 70, I guess what I would be thinking here is that there are going to be a few options. You could say, well, 70 you could rewrite as 35 times 2. You could rewrite it as 7 times 10. And that actually is going to be the one you want here. I guess you could also pick 5 times 14, but that's a weird one. And the reason that you want the 7 times 10 is because then you can cancel the 7s. So what I'm thinking here, after I've got the 3 times 7, is, okay, with 70, is there a way I can write its factorization with a 3 in it? No, 70 is not divisible by 3. Is there a way I can get it with a 7? Yep. And that's where you write it as 7 times 10, because then you can cancel that 7 and that 7, and what you end up with is 3 tenths. And there it is, simplified. And then the other one, the 64 over 40, again, just try to come up with some factorization. You don't have to nail the prime factorization. If you can, that's awesome, but you don't have to. So for 64, if I'm just trying to break that down a little bit, my first thought is 8 times 8, because 64 is a perfect square, right? It's 8 squared. So that would be my first thought here, to say, well, 64 is 8 times 8. And then I'm thinking, well, is there a way to rewrite 40 with an 8 as part of the factorization? Yeah, right? 8 times 5, that's 40. So then 8 times 5, then you can cancel this 8 on the bottom with one of these 8s up here, and you're just left with 8 over 5. And that's the answer. And I guess with this one, if you got the prime factorization, that's pretty impressive. Like that numerator would be 2 to the 6th, right? And then the denominator would be 2 to the 3rd times 5. If you can jump right to those, that's really, really outstanding. But if you can't, that's totally fine. I never really do it that way. Right? I just kind of break things down piece by piece, and then when I have pieces I can cancel out, I cancel them out. But anyway, that's it for the reduction property, at least for now. So then the next thing, multiplication and then division. So this multiplication here, we know how this is going to work, multiplying two fractions. Multiply the numerators together, you multiply the denominators together, and don't forget about that minus sign out there. So what I'm going to do is I'm going to leave that minus sign out front. That way we can't forget about it. And then I'm going to write this as one big fraction where we have the numerators multiplied, and then we have the denominators multiplied. And then we're going to see if we can cancel anything. Well, 3, 5, and 7 are prime, so they don't factor, but 6 can factor. Right? That's 3 times 2. So the numerator is still going to be 3 times 5. But then the denominator we could write as 7 times 3 times 2. And then we can cancel 3's. We got a 3 down here. We got a 3 up here. And so then leaving that minus sign out front, 5 on top, and then on the bottom 7 times 2 is 14. So it looks like negative 5/14 is our answer. Okay, then the next one is dividing by a fraction, which the usual thing to do with that is to rephrase it as multiplication by the reciprocal, which is what we're going to do. So we're going to say this is 9/10 times 25 over 18. And there is one thing I want to point out here before we go any further. The way that we did number 2, where we factored what we could factor and then canceled stuff out, it keeps the numbers a little bit smaller. And with number 2, the effect isn't really that big because you'd end up with the negation of 15 over 42 if you don't do that cancellation. And from there, figuring out that you could cancel out 3's to reduce that down to lowest terms, you'd get it, right? Like you'd see it right away with the 15. For the 42, it might take a second, but then if you went like, oh yeah, it's going to be 30 plus 12, those are both divisible by 3. So something like that, I think, you could go in the opposite direction. Here, I would not, because if you multiply these together and then try to factor from there, you're going to end up with 275 over 180. Those are big numbers, and I think it's a good idea to avoid big numbers when you can. So we are going to write this as one giant fraction. So we'd have 9 times 25 over 10 times 18. But all 4 of those numbers are going to factor. So 9 we could write as 3 times 3. And then 25 we could write as 5 times 5. And then in the denominator, 10 is 5 times 2. And then 18, I'm going to do kind of a shrewd little maneuver here. I'm going to say it's 9 times 2. And yeah, you could break that 9 down farther if you wanted and write that as 3 times 3. Or if you saw this and went, wait a minute, this 3 times 3 right here, that's a 9. So I can cancel that with that, right? They're both 9. So yeah, that'll work. And then you can cancel one of these 5's up here with this 5 down here. So then what we're left with is that we've got 5 on top, and then on the bottom 2 times 2, which is 4. So 5/4. And by doing all the factoring and cancellation, we avoid having to deal with giant numbers, which I think is a good thing. All right, next, some subtraction. And when you add or subtract, that's where you need to get a common denominator. So in order to do that, and this might be one where you can see it right away, but I'm going to do it the longer way, just in case you run to a situation where you can't see it right away. Right? The ones where you see it right away, that's easier, right? I think it's worth going through it as though we're kind of taking the rough road or taking the long path. So if we don't see it right away, you end up starting to factor those denominators a little bit. You start doing what you can. So for 60, even if you don't get the whole prime factorization, just try to rewrite 60 so it's a product where one of the numbers is prime. Because then at least you're on the right path. You're getting there. So I'm going to write 60 as 2 times 30. 2 is prime, right? So at least I'm getting there a little bit, right? I'm taking a step in the right direction. Then 18, I'm going to write as, I guess to change it up, I'll say 3 times 6. Since 3 is prime, right, we're taking a good step there. 30 could be broken down a little bit further because we could say, well, then that's 3 times 10, and 3 is prime, so we can write that as 2 times 3 times 10 for that 60. And then in the other denominator, we could say, well, 6 is 3 times 2, so 3 times 3 times 2. And then that 10 in the first denominator, you could say, well, that's 5 times 2. And that would factor it all the way down. So 2 times 3 times 5 times 2. And then the other one, I guess we're just going to leave alone for the time being. So 3 times 3 times 2. And I think it's actually going to be helpful to sort of clean up the denominators and write them using exponents. So what I mean by that is that first denominator's got a couple of 2's in it. So I'm going to write that as 2 squared times 3 times 5. And I'm going to use increasing order. So like how I have the 2, then the 3, then the 5, how those are getting bigger. I'm going to do the same thing with the other one. So I'm going to write the other denominator as 2 times 3 squared. The reason I'm writing them that way is then I can see the differences easier. Right? If they're in order and you got the exponents there, it's easier to pick those differences out. But now we got to get a common denominator. And I'll do this in a different color just to make it stick out a little. But that is what we have to do. So we have to get a common denominator. Okay, so once you have the prime factorizations here, you just need the largest power of any factor that shows up either here or here. So 2 shows up in both. We've got a 2 squared here, then this is a 2 to the first. The higher power is 2 squared, right? Then with the 3's, we got a 3 to the first right here, got 3 squared over here. So then that's going to be a 3 squared. That's the higher power. And then there's a 5 here. There's no 5 over here. So just a 5 to the first. That's the largest power of 5 that shows up. So we'll put that in there. And I guess when you multiply this all out, we are going to need that number in a little bit. It's 180, which if you did this the shorter way, you could probably see it at the beginning if you thought, well, because this number ends in a 0, I need to multiply this by something where I'll end up with a number that ends in a 0. So I will multiply by 10, and then 60 times 3 would also give you the 180. So you can get it that way too. But then let's see, here in this denominator, at least comparing to the common denominator, we're just missing a 3. And then here we're missing a 2 and missing a 5. All right, so that means that first fraction, we got to multiply by 3 over 3. So 7 over 2 squared times 3 times 5. I'm going to multiply that one by 3 over 3. And then minus 5 over 2 times 3 squared. And then here, I guess you could write this as 10 over 10, but I'm going to make this really explicit and write it as 2 times 5 over 2 times 5. All right, so then that first fraction, I guess you might as well do the multiplication and say 7 times 3 is 21. And then that would be over, well, it is 180. I guess, I got to save space here. I'm running out of space for number 4. And then minus 5 times 10, right? Since 2 times 5 is 10, that's going to be 50. And that's over 180. And then when you have the same denominator, then you can actually do the subtraction, and you'd get negative 29, right? 21 minus 50 is negative 29, so negative 29 over 180. Or if you'd prefer writing the minus sign out front, which is the more conventional way to do it, the negation of 29 over 180. And that is the answer. Okay, so like I said, I thought it was worth it to do that one the long way, although if you can see right off the bat that you're going to use 180 as the common denominator, you don't have to do all the work that I did. But I wanted to kind of illustrate this one this way of like, what if you don't see it? Like, what should you do? I figured that was, I don't know, maybe worth a little bit more, I guess. All right, number 5 is actually like number 4, but easier. It is a get the common denominator type of question, but notice we're subtracting a negative. We also write that as adding a positive. So 27 over 16 plus 2. That would be the first thing that I'd do with that. But then we need a common denominator. So here the denominator is 16. Here effectively it's 1, right? Because 2 is 2 over 1. So then I'm going to say, all right, well then this is 27 over 16. And in order to get the common denominator, I'm going to have to multiply by 16 over 16. So 2 times 16 over 16. And so then we're going to have 27 over 16. And then plus 32 over 16. And now that we have the common denominator, we can add the numerators together and we should get 59 over 16. All right, so not too bad, right? Like I said, it was the same concept as number 4, but easier. Look how much shorter that one is. All right, number 6 and number 7 are kind of a pair because you get a 0 someplace. Right? Number 6, you can see you get it on the bottom, and number 7, you get it on the top. So with 6, if you add negative 2 and negative 7, that's negative 9. But if you add negative 4 and positive 4, that's 0. So when you're dividing by 0, then this is undefined. Right? Can't divide by 0. 7 is actually the easy one because you would get 0 over 5, since 3 minus 3 is 0, and then that's just 0. So 0 on the top's fine, right? Then you just get 0. 0 on the bottom's trouble. So that I figured was worth working into this a little bit. And then let's see, we got some absolute values. One without a fraction, then one with a fraction. Okay, so without a fraction, here you would have to simplify what's inside the vertical lines of the absolute value first. So the 6 minus 10, which would be negative 4. So we can say, okay, well then this is the absolute value of negative 4, and then minus 2. But the absolute value of negative 4 is 4, so then this is 4 minus 2, which means that it's 2. Not so bad. 9 is a little bit more involved because you got to get a common denominator. The easiest common denominator for 6 and 8 I would think would be 24. So that's what we're going to do. And I guess I need to write kind of big here. So this is going to be 5/6 times 4 over 4, right? That'll get us to 24 in the denominator there. Minus 7/8 times 3 over 3. And I guess this is one where you could do it the long way to end up with the common denominator. But with a 6 and an 8, I figured that was one where I think a lot of people will be able to anticipate that one. So we can get those 24s, and then let's see, 5 times 4 is 20. So we have 20 over 24, and then 7 times 3 is 21, so minus 21 over 24. So that's going to be the absolute value of the negation of 1/24. But then the absolute value of negative 1/24 is just going to be 1 over 24. Right? And with absolute value, the way that I always think of it is its distance. Like, it's how far away is that number from 0? And distance can never be negative, right? Like, you never have a negative amount of miles to drive from one place to another, right? It's always positive, or it can be 0, right? If you don't move, right? That's a distance traveled of 0. So yeah, I mean, the way most people think about it is if you take the absolute value of a negative, then basically you drop the negative sign. That's true, but basically it functions like its distance. Like, if you think of it as being like, how far away is this number from 0, like on the number line in either direction? So it's like we're not worried about which direction it's in. Maybe in a way that's the more theoretical way to think about it, but I suppose either way would work.